We've now come to maybe the weirdest point of this section, and that's the chain rule. Okay, so the chain rule is pretty complicated. Once you've done it enough times, it's pretty simple and pretty quick and a really nice rule. But I found that a lot of times it's a little hard for people to pick up for the first time. So we're going to use it in situations like this. We want to find this derivative. There's a couple of ways that we could do it. We could write this as a product. This times itself. That's what it means to be squared. And then we could use the product rule. Or we could FOIL it all out and then just use the power rule. So we have some tools of doing this. What we don't have tools yet is what if there's not just being squared and there's two of them? What if there's 20 things multiplied by each other? Well, that's where the chain rule is going to come into play. So leave this space blank for now, and we'll show the different ways of doing this. Going to introduce the chain rule. We have two different ways of doing the chain rule. One way is with the Leibniz notation. Remember, this is Leibniz notation. This says the derivative of y with respect to u, the derivative of u with respect to x, or in other words, take the derivative of u, and I'm telling you that x is your variable. Then there's also the Newton notation, which is looking like this. So the chain rule is what we use for function composition. If we have a function inside of another function. When I say that, what I mean is we have an inside function here. And then what's happening to that inside function? It's getting squared. So that's the inside and the outside function. The outside function is the squaring function. The inside function is this polynomial. Whenever you have an outside and an inside function, you'll use the chain rule. So we can visualize it here. G is our inside function. And f is what is being done to the inside function. So f is the outside function. So we can write the inside function is just something u, and then f of u is the same thing as f of g of x, because u is the same thing as g of x. It's just some notation. Then there's kind of two ways of doing this. Let's just do the problem both ways with this notation and see what happens. All right. So let's scroll up to here and try to use this notation. Y is some function being applied to u, and u is that inside function. Let's say, and we're going to do it two ways. First with the Leibniz notation, and then with the Newton notation. So with Leibniz notation, that says u is our inside function. So write u as the inside function. U is that 4x cubed plus 15x. Now y is just what's happening to u. What is being done to u? Well, if this is u, why is u squared? Why is that? Well, y is this whole thing. And if u is the inside function, it's this thing squared, and this thing is u. So that's all that this is trying to say. Y is u squared, and u is this other function. If you plugged in u, took the function composition, you'd get the original function up here. So what the chain rule says is dy dx, which is what we want. We want the derivative of this function with respect to x, is dy du, the derivative of y with respect to u, times du dx, the derivative of u with respect to x. We've already done the weird, messy part. Now it's the easy part. What is the derivative of y with respect to u? Well, that just says take the derivative of y, and I'm telling you, u is the variable. Just a power rule. 2u. du dx says take the derivative of u with x as the variable. So what's the derivative of u if x is our variable? Power rule. That's going to be 12x squared plus 15. And we're pretty much done. All that's left is to put it in terms of x. Once we do that, we know that u is 4x cubed plus 15x. And, oops, don't quite have enough room. Story of my life. We multiply, right? 2 times u is this, and that's getting multiplied by this. The 12x squared plus 15. And that is our answer. We could factor it a little bit. We could clean this up a little bit. But in general, that's what the chain rule looks like. Okay. Now, Newton's notation's a little different. This says that, let's jump right to this. The derivative, and the chain rule in words is also useful. The derivative of our function is what happens when we take the derivative of the outside function, leave the inside alone, and multiply by the derivative of the inside function. So, what happens if we take the derivative of the outside function? Again, this is our outside function, is the squaring. So when we take the derivative of the outside function, we get 2, right? It's the power rule. We leave the inside alone. And then it says we need to multiply by the derivative of the inside function. What's the derivative of the inside function? 12x squared plus 15. And you can see that our answers match. Derivative of the outside function, leave the inside the same, multiply by the derivative of the inside function. That's what we just did. Of course, you can see that there's fewer steps in this blue method, in the Newton method, but I think the red method is usually more straightforward. Still totally confused? That is fine. I've got another example coming up for you that we're also going to do both ways. Chain rule in words is written down right here. That's what I'm verbalizing when I'm going through it. Most people, once they've done the chain rule enough times, do just go directly to here. And we all say this in our heads. Pretty much all of us. Okay? Even to this day, I still say that in my head. Let's do another one with both methods. Okay? So we'll do Leibniz method over here. It's the same method, just different notation. And Newton notation over here. So first off, anytime you're doing a chain rule, you need the inside function and you need an outside function. But just like before, our inside function is going to be u. And the outside function is going to be what's happening to it. Okay? It's going to be the exponent in here. I'm trying to stay consistent with my notation. Yeah, outside function is getting raised to this exponent. So, what we're going to do is we're going to say, okay, y is the outside function. Oops, I tried to switch colors. Y is the outside function when we plug in the inside. U is the inside function of 4q cubed plus 15q. You're going to see a lot of similarities. So what is our outside function? It says we're taking u and we're raising u to the 20th power. That's what y is. We're looking at u, is this guy here. We're raising it to the 20th power. Anytime you set this up, you plug this in for u, you should always get the original function. All right. And now we've done the hard part. This this time, we won't say dy dx. Why not? Because our variable is q. The derivative of y with respect to q is going to be the derivative of y with respect to u times the derivative of u with respect to q. You always forget what order this goes. You can check your notes, or you can think of cancellation. These aren't actually fractions. They don't actually cancel, but the notation is intentional, and it's a good way to remember it. And now we just write it all out. What is the derivative of y with respect to u? Take the derivative of y, where u is the variable. We use the power rule, 20u to the 19th. Times the derivative of u, where q is the variable. That's going to be 12q squared. Remember your parentheses. Plus 15. The last step is just plugging in u, putting everything in terms of the original variable. 20 times u, which is 4q cubed, plus 15, q. And then that's to the 19th power. And then we multiply it by this other guy over here. 12q squared plus 15. And again, there's some tiny things you could do to clean this up, but that's not very important to me. Most of the time when I give you these really messy problems, I'll probably just tell you you don't have to simplify for like quizzes and stuff. And hopefully at this point, you get a little bit more comfortable. We can look at it with the Newton notation. Take the derivative of the outside function, leave the inside alone, multiply by the derivative of the inside. We do that, the derivative of the outside function is the power rule. Bring the 20 down, change the 20 to a 19. The inside stays the same. Multiply by the derivative of the inside. What's the derivative of this inside? Use the power rule. 12q squared plus 15. And again, you should see that our two derivatives are identical. We got more examples with messier problems in the next one. Get some practice as well, and let me know if you have questions. Bye-bye.